site-specific documentation, prepared by a locally registered structural or civil engineer with their signature and stamp, would include the project address, as well as the applicable seismic criteria for that location, as assimilated from the IBC, ASCE, and the USGS. It would also include the manufacturer's Seismic Qualified Certificate, which must contain the name of the independent third-party seismic testing laboratory used by the manufacturer to validate the certificate, with the test methods and procedures employed. So now, let's take a closer look at how the equipment is seismically qualified to receive a certificate as shown in method number 2 by one of these three procedures: A, analysis, or B, testing, commonly referred to as shaker table test, as defined in section 13.2.5, or experience, data as defined in section 13.2.6. The first approved method is by analysis. Let's see what analysis really means. As defined by a well-respected dictionary, analysis implies that assumptions or simplifications will have to be made. Therefore, it has an inherent margin for error. As for the ASCE 7-05, many sections contain parts that can be assimilated to define analysis, such as: analysis requires that a mathematical computation be made of the dynamic forces from a minimum of 3 degrees of freedom and are based on a 3D model of that equation. Analysis also allows for different standards that could be used for computation, thus allowing for additional error or bias. Eaton recommends that IEEE 344 be used as a basis for the computation. However, there are unknowns that come into the equation that can only be ascertained by actual test, such as the natural frequencies that occur in the equipment. Hence, it is extremely difficult to derive an absolute factor for these natural frequencies of the equipment based on mathematical assumption. Therefore, many design professionals rely on the equipment manufacturer to provide data for analysis based on actual test of equipment, where absolute values can be derived from the data collected at accelerometers that have been placed on the equipment during the test. However, it should be noted that analysis with actual test data is extremely useful for the manufacturer in modeling equipment variations from that of the actual test unit. Let's see how this is done. First, the test data is recorded. Then the software models the results based on the various points of reference on the equipment provided by the accelerometers. That data is then analyzed at the specific stress points and their ability to withstand a seismic event. Then this data, via the software, can be utilized to model the various combinations that occur in that product platform or family of equipment. Now let's move forward to the next approved method for equipment seismic certification, that is, by test. A test is done by securing the equipment on a triaxial shaker table, that is, a test platform device with simultaneous motion in the 3 axes of vertical, side-to-side, and front-to-back motion. That simulates a seismic event based on the input of specific criteria to determine the seismic capacity of the equipment. Here is what an actual test looks like. But you still might wonder, why test is better than analysis? As noted here, a test can include either the actual equipment to be used on the project or a sample of a representative equipment that is similar in nature and part of a product platform or family. Absolute values can be recorded from the accelerometers on the test equipment to provide actual natural frequencies. A test determines, by proof, the type of mounting to be utilized for the installation of the equipment. It also verifies that the actual condition of the equipment would be after a seismic event. In Eaton equipment, you can also be confident that evaluation includes testing to a higher standard than the code specifies. This allows for a comparison based on hard data of the RRS, or the required response spectrum, with the TRS, or test response spectrum. Let's see what this looks like. As can be seen on the right of the screen, a piece of equipment subjected to a shaker table test with triaxial motion for 30 seconds covers a worst-case scenario seismic event compared to the spectrums on the left from the 1994 Northridge earthquake in California. Hopefully, this removes any doubt as to the superiority of testing equipment for seismic qualification. But you may wonder, who does the testing? ASCE mandates that testing must be performed by a third-party independent testing laboratory and not the manufacturer of the equipment. The test shall be based on a nationally recognized procedure acceptable to the AHJ, and the results must be equal to or greater than the project site-specific demands, or RRS. So now let's look at the third approved method for seismic qualification of equipment, called experience. Shown here is an example of equipment that perhaps would have to qualify by the experience method. It might be due to the unique nature of the installation and interconnection of components, or perhaps the equipment is such size and weight that it cannot be accommodated by a shaker table. But caution is in order if one selects this method. It is difficult to prove. Let's see why. By experience means that an existing equipment installation would be similar in nature to the new equipment installation, has a history of documentation proving that the equipment has been through similar seismic events that match the criteria of the new installation, is anchored in a similar fashion as proposed, that the performance over time has been evaluated by accepted engineering practices, and that if any failure has occurred, the root cause of that failure has been determined by experts based upon the chronological documentation. If that criteria has been met, and it is extremely unlikely that such accurate records were kept in the fashion necessary, then the new project seismic criteria would have to be equal to or less than the existing installation. As you can see, the experience qualification method is a difficult one indeed for one to meet all of the criteria. Let's now cover another important area that needs to be considered due to the legacy of the 1997 UBC standards. Under old UBC, the calculation method based on static forces was acceptable for providing seismic certification to equipment. This method is no longer valid under the new IVC and CBC for ASCE 7-05 requirements, and thus makes any manufacturer's reference to that standard invalid as the basis for their equipment being seismic qualified. Therefore, the intent was missing from the UBC, demonstrating a seismic event by simulation that the equipment could withstand the dynamic demand. Many small OEMs or original equipment manufacturers simply cannot afford the testing required to meet the new standard. Therefore, it is imperative that the consultant, the contractor, the end user, and especially the AHJ be informed as to what documentation is the proof and basis for the seismic qualification certificate. Many reputable OEM firms that have been in the industry a long time still advertise that they are seismic qualified, but further in-depth research often reveals that this statement is based on the old UBC calculation static force method and is no longer valid. Another reason this would no longer be valid is from an additional carryover from the outdated 1997 UBC, and that is of seismic zone maps. Usually one would have to be in seismic zone 3 or 4 before seismic qualified equipment certificates were required. However, as we reviewed earlier, the new IBC and CBC standards require that project-specific or site-specific seismic demand criteria be utilized. Let's see why. We have learned from the infamous 1906 San Francisco earthquake and from recent seismic activity. Large geographical areas covered by the outdated 1997 UBC zone maps are simply inadequate to give a true picture of the seismic demand at a particular location. Here's why. This information is from 3 different seismographs placed around the same city, Northridge, California, which clearly shows 3 different results of seismic activity during the January 17, 1994 earthquake. Some would argue that, like the old UBC zone designations, couldn't we just use zip codes or some broader classification than site-specific based on longitude and latitude or site address? These 3 seismographs were not only from the same city, but also the same zip codes. Therefore, soil types and proximity to fault lines have an impact on the seismic event demands, which can vary greatly in a very small geographical area. We have also learned that not only the geographical location of the equipment is critical, but also where the equipment is located on that geographical site. It becomes obvious when we compare the seismic demand motion of ground level located equipment with that located on the roof. As can easily be seen in the seismograph on the right-hand side of the screen, the magnitude and duration are of a greater demand at roof level than at floor level. The next topic we need to now consider and appreciate is this. The seismic qualified certificate is only as good as the installation employed at the project site. One must remember that equipment must be installed per the manufacturer's recommendations as found in the installation manual provided with the equipment. This requirement is also found in the 2008 NEC and CEC at 110.3b and 110.13a. It is up to the AHJ, whether the electrical or structural principal, to verify that these installation guidelines have been followed. Some manufacturers even supply special hardware where seismic qualified equipment is required. This hardware must be utilized to maintain the seismic qualified rating and certificate. It must be noted that although the manufacturer will instruct the design professional and installer as to the diameter and location where the anchorage or attachment should occur, it is up to the locally registered civil or structural engineer to determine the type and depth of embedment of that attachment or anchorage.